Now we're live. Okay, so today, 3/8/19. Today, what we want to talk about is rationalizing the denominator of root fractions. Okay. Let's just go straight with this word, rationalize. Go and write that down, okay? Rationalizing the denominator of root fractions. And I don't ever expect you guys to know all the math fancy words, but someday somebody in college might. So rational, okay, to be a rational number. Rational numbers are any numbers. A rational number is any number that can be a fraction. Any number that can be a fraction, okay? Okay, so that's a rational number, okay? So for instance, 1/2 is a rational number, okay? 0.5. 0.5 is a rational number, right? 3 is a rational number, right? What isn't a rational number? Pi. Pi is not a rational number because you can't make pi into a fraction. Why can't you make pi into a fraction? Because it goes on forever, right? That makes sense, right? And square root numbers are irrational numbers. Square root numbers are irrational unless it's a perfect square root, right? I mean, like the square root of 4, square root of 9. But square root of 2 goes on and on and on. It's 1.41, blah, 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 blah. So you've got pi is an irrational number, and you've got any square root number or cubic root or whatever is also an irrational number, okay? So if I look at what I want to do, I want to rationalize the denominator, which means I want to get the square root out of the bottom of a root fraction. And so if I take a look at example 1, example 1 is pretty easy because 16 is a nice number. So example 1 is the easiest of all. That's really like the square root of 9 over the square root of 16. And this one rationalizes pretty easily because 16 is a perfect root. Square root of 9 is 3. Square root of 16 is 4. 3/4. Boom. A freshman could do that one, huh? There you go.
What about the 8th graders?
Piece of cake for an 8th grader too, huh? Yeah.
What about the juniors?
How about a 6th grader? I think even a 6th grader could do that one. You guys agree? Yeah. Now, example 2 is a little bit different because there is no square root of 5. In fact, the square root of 5 is an irrational number. If you take a look, you go the square root of 5. You know, here it is. 2.236067977, and it keeps going. It keeps going on forever. So it is an irrational number. So here's how we fix it. We're going to fix. I'm going to fix the problem with the problem. Okay. Fix the problem with the problem. Now, if you've had me before, you know exactly what I'm talking about. If you've never had this before, in a second I'm going to show you what it means. Okay. So here's the problem. The problem is you have a square root in the denominator. That's the problem. So if you fix the problem with the problem, what I'm going to do is multiply both top and bottom by the square root of 5 over the square root of 5. Okay, and I'm going to show you why that works. So you fix the problem with the problem, okay? So if I multiply by the square root of 5 over the square root of 5, I'll have a 3 square roots of 5 over the square root of 25. Okay, and I'm not done because you know where I'm going to go from here, but you know, if you multiply by the square root of 5, because the problem is the square root of 5, right? So if I multiply by square root of 5, Daisy, you were way ahead of me. It just makes 3 square roots of 5 over 5. Now, don't divide these numbers. That is not a 5. I know, you say, yeah, it is, Mr. Davis. No, that's not. That is 2.2360. This is not 5. You guys agree? That is 2.23 blah, blah, blah. So that is your answer. Now, as far as the value, and this is where it'll be interesting to see what happens when you go to college, because there are some math teachers in college that don't mind this answer. Most of them will want you to rationalize, okay? So it just depends. It's kind of a picky little rule because they have the exact same value. And this one looks nicer, doesn't it? But it's just the rule in math, okay? So these two have the same calculator value, but this one does not have a square at the bottom, right? Okay, so let's look at number 2, or number 3. So the problem with number 3, let's first rewrite it. Square root of 5 over the square root of 7, right? Again, we have a square root in the denominator. So let's fix the problem with the problem. So I'm going to multiply top and bottom by the square root of 7 over the square root of 7, right? We wind up with square root of 35 over 7. Do you mind if I skip that step? I mean, we're in Algebra 2. Square root of 7 is 49, which makes 7. You guys agree with that? Everybody okay with that? Okay, square root of 49, which makes 7. Okay? Yeah, and don't divide those, because that is not a 35, is it? No, it's not 35. It's some ugly decimal. 5.9, blah, blah, something like that, right? Exactly. Okay. Now, example 4 is a little bit different. So what we want to do is at the very top, way up here, let's write our perfect cubes. Let's make a list of our perfect cubes, okay? All right, we don't have to have them all, but if I have a few of them. So first of all, the very first perfect cube is 1, but I'm not going to write 1 because I know the cube root of 1 is 1. We agree? Okay, so what's our next one? How about 8? 8's a perfect cube. Because what's the cube root of 8? 2. What's the next perfect cube? 27. Because what's the cube root of 27? Good. What's the next perfect cube? I think it's 64. And then 125. I think it's 216, isn't it? 216. And then, is it 343?
Yeah.
Is it 343? And then we'll go one more. 512? Do we have a calculator? Is it 512? Let's double check. Are you sure? What is 8 cubed, you guys? Are you doing it? Ledger, are you doing it?
512.
Is it 512? And that's probably all the further we need, okay? Now these are our perfect cubes, right? So let's take a look at example 4. We are not going to multiply by 4. We are not going to fix the problem with the problem when it becomes a cube. What we need is this bottom number to be a perfect cube, okay? So I need the bottom number to become, what number should I make it? 8. How about we make it 8? Okay, so if I make it a cube root, I want to make it a cube root of 8, because cube root of 8 is, we can do that, right? So what do I need to multiply by? Cube root of 2. You agree with that? So I'm going to multiply both top and bottom by the cube root of 2 over the cube root of 2, which makes a perfect cube on the bottom. I'm going to get the cube root of 4 on the top. And on the bottom, the denominator, I'm going to get the cube root of 8. Okay? And then the cube root of 8, we know that. That's 2. It's a perfect cube. So in the denominator, we get 2. And the numerator, you get the cube root of 4. So a root on the top is okay. A root on the top is okay. It follows the rule. But a root on the bottom isn't, so we rationalize the denominator. Okay? That one's a little bit harder, right? Now, example 5 is a little bit different, slightly different. So all we want to do is just simplify this as much as we can. So I'm going to multiply exponents. I'm going to get a 3 to the 2 fourths. You okay with that? Yeah. 3 to the 2 fourths. So I got the 2 fourths. Or 3 to the 1/2, which is fine. Or we can just call it the square root of 3. Either one of these two answers. See what I did? I just multiplied exponents, okay? Yeah. I did 1/4 times 2. So 2 on the side, 2 times 1/4, right? 2 over 1, I get 2 fourths. You guys see that? And then I reduced it, okay? Now, 6 looks a little bit confusing, but let me do a little side work that you can do that you totally will understand. If I had, just ignore that. If I had x, just say x to the 5th over x squared, what would you do? Right here, what would you do? Subtract exponents, wouldn't you? Right? You'd subtract exponents, that makes sense. Well, 10, this number has an exponent. What is it? 1. Totally right. So if we went 10 to the 1/5 minus 1. Okay, let me just write it that way because I'm going to subtract exponents, right? So I'm really going to take 10 to the 1/5 minus 1. So this is up in the exponent, okay, which is going to make a 10 to the negative 4/5. How's that? And we're going to leave it like that.
So we're not going to make it into a fraction.
We could. We could make it 1 over 10 to the 4/5. That's okay too. Either answer. Either answer. How's that? Okay, example 7. Let's just multiply exponents, okay? Let's multiply. I'm going to multiply exponents. So I'm going to get a 3 to the negative 4/4, which is a 3 to the negative 1, which is 1/3. Hey, we're getting good at this stuff, aren't we? Man, we are getting smart. So smart. Okay, example 8. Let's do what's inside first. Let's just take care, let's tidy up what's inside, right? So, little side note, okay. If you had x, little side note, just if you had x to the second times x to the third, what do? Right, x to the 5, you guys agree? So let's add exponents right here. Let's add exponents first, okay? So I'm going to get a 2 to the negative 3/4 plus 1/4 first, okay? Let me do that first, okay? So I'm going to get a 2 to the negative 2/4, you okay with that? 2 to the negative 2/4, okay? Which I could reduce, right? I'm going to do it in a second. How about if I multiply exponents right here? So we're going to 2 to the 2/4 to the positive 2/4. Does this make sense? I'm going to multiply, which is 2 to the 1/2 or the square root of 2. Either answer. Yeah, Gavin.
Ignoring the other two, like multiplying.
Oh, that 2
Yeah.
right here? Yeah, so let me ask you back, real super easy question. How many x's do you see?
2.
But when I multiply it, what do you see?
No.
Does that make sense? I mean, it's the same thing here with the 2's, right? Right, got it? Okay, good question. Okay, turn the page. Okay. Woo, man, what do you think? Well, how about this? What are my special numbers? 1, 8, 27, 64. So I'm going to write those up there. 8, 27, 64, dot, 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 dot. I think the 20, I'm going to circle the 27 in this case, because I think I'm going to need, with the 8 and the 9, I think 27. Does 27 make, like, we're going to see some 27s in this? With an 81 and a 9, does that make sense? Oh, because this would be so much easier. I can do this so much faster. Cube root of 27 times the cube root of 3. You okay with that? Times the cube root of 9. Yes, you can. I just like to be fancy-dancy math guy, huh? Okay, here's my 81. You okay with that?
Yeah.
Now, that is 3 times the cube root of another 27, right? Yeah. 3 times 3 is 9. Daisy, do you see how fast I got that by just being a fancy-dancy math guy? Yes, Daisy.
When I just multiplied it, I got the cube root of
729?
729, and I know because 81 times 9 is just a cube root.
You are absolutely,
9 to the third, I just
Yep.
discussed it.
you are completely correct in what you did. How's that for an answer? Okay. All right, how about 10? How about some fancy-dancy math? Now, before I do anything, I can make this problem easier. I can make it easier. That's a cube root. That's a cube root. Does 2 go into 50?
Yeah.
Now, let me just rewrite it in a little ways, so you'll see what I'm talking about. Okay, let me just rewrite it. You don't have to rewrite this, but I want to show you. Since they're both cube root, I can make it a big cube root of 50 over 2. Does that make sense? Which is 25. You guys okay with that? Okay, so then I can rewrite this as cube root of 5 times the cube root of 25, which would be the cube root of 125, which is what? 5. Okay. How's that? Yeah, Daisy?
So we have to have 5 cubed over 2 cubed.
Yes, and I rewrote it like that. Mm-hmm. Yep, yep. Gavin.
I got it.
Okay, good.
Stupid question.
No such thing as super. Now, if I look at an example for it first, I'm kind of intimidated. I'm like, whoa, I got to the 8th powers and to the 4th powers. I'm like, what's going on? So let's just see if I can do anything with this. Okay, so first of all, on the bottom, I kind of see something. I kind of got a hint on the bottom. What if I make this an 8th root of 3 squared? Okay, 3 squared. I know, you're like, why don't I make it 9, right? Why don't I make it 9? Anybody know why I'm going to do it this way? Because this is the same thing as a 3 to the 2/8, isn't it? Which would be a 1/4. So really what I have is a 4th root of 3 on the bottom. How's that going to help me? Well, I've got 4th roots up here, right?
Oh, yeah,
Look at that. That was my motivation. Is I wanted to make them all 4th roots so I can put them all together, right? So that was my motivation, is to get to a 4th root. So I've got 4th root on top. So let's go. I got a 4th root of 4 times a 4th root of 12. Okay? All right, now what? I'm going to get a 4th root of 48. Or let's do this. Oh, let's make this even easier. I see something else. I do. I know, I have a sick mind, don't I?
What the heck?
Okay, 12. 4 times 3, right? Why would I want to do that? Hopefully you see it. If you don't see it, then you got to be blind. You guys agree? You got to be blind, right? You agree with that?
They divide me. So that makes
Right.
1.
So then I got the 4th root of 16, right? See where I got the 4th root of 16? And guess what? 2 times 2 times 2 times 2 is what?
16.
Boom. There's your answer.
That one seems easier.
That was a...
That was a problem that makes you think a little bit. I like those. Does that make your brain work a little bit? I like that one, okay? All right, so here's what we've got.